Section 7.3 is all about simplifying radicals and the Pythagorean Theorem. So if a and b are real numbers and n is a natural number, then it's always true that if I'm taking the same root, so the nth root of a and the nth root of b, that's the same as taking the nth root of a times b, i.e. the root of a product is the product of the roots. Okay? So let's go ahead and work through a few examples. If I have the square root of 5 times the square root of 7, that's going to give me the square root of 35, because 5 times 7 is 35. If I have the square root of 11 times the square root of p, that's going to give me the square root of 11p. If I have the cube root of 3y and the cube root of 12z, that's going to give me the cube root of 36yz squared. I like to write my variables in alphabetical order. And if I have the sixth root of 10m to the fourth times 5m, that's going to give me the sixth root of 10 times 5, which is 50, m to the fourth times m, which is m to the fifth. Now, there's also a quotient rule for square roots, and I've done this in class and showed you that the radical does distribute over fractions, right? But now you know that it's a rule. So as long as a and b are real numbers, and b doesn't equal 0, and n is a natural number, I can take the square root of a quotient, and it's the same as the quotient of the square roots. But it doesn't have to be a square root. It should just say like the root, right? Because I could take a cube root, I could take a fourth root, and this would still work. So a few examples. If I have the square root of 49 over 81, that's the same as the square root of 49 over the square root of 81, which would give us 7 over 9. If I have the fourth root of 81 sixteenths, that's the same as the fourth root of 81 over the fourth root of 16. The fourth root of 81 is 3. The fourth root of 16 is 2, so I'd have 3 halves. If I have the square root of 6/49, that's the square root of 6 over the square root of 49. I can't simplify that just yet, right? So I've got the square root of 6 over 7. If I have the cube root of negative 8 125ths, that's me the cube root of negative 8 over the cube root of 125. The cube root of negative 8 is negative 2. The cube root of 125 is 5, so I get negative 2/5. What's hardest for some students is remembering that you need to simplify radical expressions of non-perfect roots. So what does that mean? So let's say I have the square root of 20. I want to factor 20, so I find that 20 is 2 times 2, morning Bobby, times 5, which is 2 squared times 5. Now I can go ahead and put that under the radical. I'm grouping squares because we're taking the square root. Remember that square roots cancel out squares. So this is the same as the square root of 2 squared times the square root of 5, right? We learned we could pull this apart with our product rule. Well, the square root of 2 squared is 2, so I would get 2 square root of 5. Okay, let's go ahead and do the same for 24. So 24 factors into a 3 and a 6. No, a 3 and an 8. And 8 factors into a 2 and a 4 and a 2 and a 2. So I have one perfect square. So 24 is the square root of 2 squared times 2 times 3. I want to pull out that perfect square. So I'd get 2 square root of 6. Let's take another look. Let's look at 108. 108 factors into 2 and 54, which factors into 2 and 27, which factors into 9 and 3, which factors into 2 3s. Okay, so I've got 2 squares here. I've got 2 squared and 3 squared. So 108 is the square root of 2 squared times 3 squared times 1 left over 3 all by himself. That means I'm going to have the square root of 2 squared times the square root of 3 squared times the square root of 3. And again, you don't have to write this extra step if you don't want to. It's just what I do, right, to make sure we're all on the same page. So I get 2 times 3 times the square root of 3. So I get 6 square root of 3 as my final answer. Let's take a look at the square root of 15. 15 factors into a 3 and a 5. There are no duplicates. So I can't simplify that any further. So it's already fully simplified. Next, let's take a look at 16. That factors into a 2 and an 8, a 2 and a 2, a 4, and a 2 and a 2. Now, I'm not taking the square root of 16. I'm taking the cube root. So instead of collecting squares like I did in the first 3 problems, I need to collect cubes. And I've got 2 cubed times 2. That's going to give me the cube root of 2 cubed times the cube root of 2, which is 2 cube root of 2 as our final answer. So let's go through some more examples, some that involve variables. So if I have 16 square root of 16m cubed, well, I know that I'm going to have the square root of 16, which is pretty easy because that's 4, right? That's going to be times m cubed, but m cubed is really m squared times 1, right? We've got to pull out the perfect square. If I had wanted, I could make a factor tree of all the m's and collect the set of 2. So I've got 16m squared times m. That means I'm going to have 4, because the square root of 16 is 4, m, because the square root of m squared is m, square root of m. Okay, let's try this again. If I have 200, that is 2 times 100, which is 2 times 50, which is 2 times 25, which is 5 times 5. So I've got 2 5s, 2 2s, and 1 2 left over. And I have k to the 7th. So that means I'm going to have k squared times k squared times k squared times k. Okay, I've got q to the 8th, which is q squared times q squared times q squared times q squared. So I have 2 squared times 5 squared times 2 times k squared times k squared times k squared times k. Again, you don't have to break this apart if you can start to see the pattern. Times q squared times q squared times q squared. Okay, that's going to give me the square root of 2 squared gives me, let me erase a little bit of this. Okay. So this gives me a 2. Square root of 2 squared is 2. Square root of 5 squared is 5. I've still got a 2 in my radical. And then I've got a k, so that's k cubed. But I have a k under the radical. And then I have 4 q's. So my answer is 10 k cubed q to the 4th square root of 2k. That's my final answer. Okay, let's take a look at the cube root of negative 8x to the 4th y to the 5th. I'm going to go ahead and clear my workspace and change my pen color because it's what I feel like doing. So if I have the cube root of negative 8x to the 4th y to the 5th, instead of breaking things up into squares, I'm breaking them up into cubes. So I now have negative 2 cubed, x cubed times x, that still gives me x to the 4th, y cubed times y squared, okay, but I'm taking the cube root, so I'm going to have a negative 2 x, and an x still under my radical, and then a y, and then a y squared, still under my radical. If I want to take the 9th root of 5 to the 6th, I can't do that, right? I've just got 5 to the 6th. If If I want the fourth root of p squared, also can't simplify that. I mean, I guess I could write it as p to the, oh, okay, that's what I was supposed to do. Sorry. Okay, so why don't we rewrite these as rational exponents? So if I have the ninth root of 5 to the 6th, that's the same as 5 to the 6th times 1/9, aha, which gives me 5 to the 6/9, which is 5 to the 2/3, which is different. So we've simplified it a little bit. So I have 5 squared, the cube root of 5 squared. Let's do the same thing with p squared. So if I have the fourth root of p squared, that's p to the second power to the 1/4. That gives me p to the 2/4, which is p to the 1/2, which is just the square root of p. Now here I have the square root of 7 times the cube root of 2. Friendly reminder, I can only multiply them if they have the same power, which they do, or if they are of the same root, which they are not, so I can't simplify this expression any further. The last thing I'm going to talk about in section 7.3 is the Pythagorean Theorem. So the Pythagorean Theorem states that for a right triangle, meaning this is a 90-degree angle, with sides ABC, the following statement holds true, where C is the hypotenuse. I misspelled that. Hypotenuse, also known as the longest side. Okay? So I have that a squared plus b squared equals c squared, and we can use this to solve for c below. So let's let 4 equal a and 6 equal b, and we're going to solve for c. So if I have 4 squared plus 6 squared equals c squared, that's going to be 16 plus 36 equals c squared. That means 52 equals c squared, and I want to take the square root of 52 and the square root of c squared to get c all by itself. So 52 factors into a 2 and a 26, which factors into a 2 and a 13. So I've got the square root of 2 squared times 13. So my final answer for c is 2 square root of 13. We also have the distance formula. This is another formula that involves radicals. What this does is this allows us to calculate the distance between any 2 points on our coordinate plane. So that's pretty cool. So what you're going to do for the distance formula is you're going to take the square root of your change in x plus your squared plus your change in y squared. So here's our example. If I have d equals the square root of -6 minus 3 squared plus 5 minus a -4 squared. That gives me the square root of -9 squared plus 9 squared. That's me the square root of 81 plus 81, which is the square root of 162. Well, 162, not surprisingly, factors into a 2 and an 81, and 81 is 9 squared. I'm not going to break it down any further. So I have my distance is the square root of 9 squared times 2, so I get 9 square root of 2 is the distance between these 2 points. And it's not always that the distance is going to come up to be a radical, it's just pretty darn common.